So now that we've discussed a bit about linear modeling, let's move on to generalized linear modeling. Generalized linear modeling is, of course, just a generalization of linear modeling. It's more or less the same mathematics with some extra math on top that permits some added flexibility about certain assumption violations, the distribution of residuals, the model fit. And so basically generalized linear models, or GLMs, really just allow you to model data which violate some of the assumptions of linear models. Turning back to these 6 model assumptions that we've discussed for linear models, that it needs to make real-world sense, it must be additive, it needs to be linear, and that the residuals or errors must be independent, homoscedastic, and normally distributed. GLMs allow you to accommodate violations of assumptions 1, 3, 5, and 6. Right? If you've got violations of assumptions 2 and 4, that's beyond the scope of this course. You're going to need nonlinear modeling or hierarchical or mixed effects modeling, respectively. But GLMs are a really powerful tool that we can use to accommodate data which violate 4 out of these 6 assumptions. And so I agree with kind of a lot of other statisticians and data scientists and whatnot about using GLMs over some alternative approaches that are commonly advocated for. If you think back to this chart that I showed you previously of kind of a flowing through from your types of data that you're trying to model to what your questions are and ending up with a certain statistical test to run, this kind of common way that statistics is taught, if you look at this chart closely, you'll see that each of kind of the main statistical tests is shown with a parametric version and a non-parametric version. What this means is that there is a version, the parametric version, which kind of ascribes to the 6 assumptions of linear models, right? It makes those assumptions and it holds you to them. The non-parametric version of these tests does not make those assumptions. It ignores those 6 assumptions through a sort of workaround where instead of assuming a normal distribution, it doesn't assume any distribution at all, which is why it's non-parametric. There are no parameters in the sense describing a distribution because it simply ranks the observations kind of ordinally in order and runs tests that way. So instead of comparing for example, a t-test where you've got 2 groups of data and you're comparing a certain value. Instead of saying, like a parametric t-test would, that those data come from a normal distribution and comparing those distributions, the parameters from those distributions, a non-parametric version of a t-test, a Mann-Whitney U-test, for example, simply ranks the observations in those 2 groups and compares them that way. So there's no need to say anything about parameters of a normal distribution. This is a common way that people get around the issue of violated assumptions. They just switch over from using a parametric test to a non-parametric test, a parametric model to a non-parametric model. However, non-parametric statistical tests, while they are widely applicable and they're so general because they don't make any assumptions at all about distributions, they're actually a bit weaker than parametric tests are, right? If there's a real effect there, you're less likely to find it with a non-parametric test, right? Parametric tests are more powerful. And so that decision to move from a parametric test to a non-parametric test should not be taken lightly. You should think about the fact that you are going to lose statistical power, the ability to identify a real effect, if you make that shift. And this is a big reason why I would say that GLMs are preferable to non-parametric tests. GLMs are parametric, right? They do make assumptions about parameters describing different distributions. The difference between a GLM and what is conventionally considered a parametric test is that a GLM can accommodate non-Gaussian data or residuals, data that are not just normally distributed. And it allows you to do this without the loss of power that's associated with shifting to a non-parametric test. So GLMs are really, I think, the preferred way when you've got model assumption violations. Switch to a GLM, not a non-parametric test whenever you can. Another common way that people advocate for handling model assumption violations is transforming your data. If you don't want to switch over to a non-parametric test, you can apply, for example, a log transformation or a square root transformation to your data. And this will have the effect, it can have a certain number of effects in different ways, but it can allow you to then use a linear model that makes assumptions of normality in a lot of cases. However, transformed data are actually pretty difficult to interpret in a lot of cases, and models that are based on transformed data can actually lose statistical power. For example, this plot here, these two plots, the one on the left shows kind of the regular linear relationship between population size on the y-axis and distance on the x-axis. If you log transform those variables, right, because a population size is bounded by 0, as is a distance, so they can't actually be negative. A log transformation can help you accommodate that, but in doing so, you're making this plot a lot more complicated, right? It's a lot more difficult to interpret what's going on in this figure than it is in the first one. So log transformed data or any other transformed data can allow you to get around issues with assumption violations, but it's problematic, right? There have been numerous papers out, this is the title of just one of them, showing that huge numbers of scientists struggle with interpreting plots like this. And so GLMs, what they allow you to do is include data transformation, but it's doing it internally and really only for the model fit itself, that deterministic part of the model. And so a GLM permits you to visualize the model on the untransformed scale, on that kind of real scale that you collected the data on, but still then specify that you've got some perhaps non-Gaussian distribution of your residuals. And here I've got another title of a paper thrown up. The arc sign is asinine, which is a well-known paper in ecology arguing that transforming your data is problematic because it's more difficult to interpret and you lose statistical power in a lot of cases when you do it. GLMs are a much better option. So breaking it actually down here and looking at the linear model that we've talked about before, right? We've got the deterministic part and the stochastic part. In the deterministic part of the model, we're trying to predict mu based on adding these different coefficient estimates, beta naught, beta 1, and so on, and multiplying that times our predictor variable. We're then taking that mu value, plugging it into, in the case of a basic linear model, a normal distribution, and that's what produces the actual data that we've got on the y-axis. The actual data are normally distributed based on that mathematical equation that we've got in the deterministic part. So in this case of a linear model, the model is a straight line, right? It's fitted as a straight line through your data, and the errors around it, the residuals around that model fit, are normally distributed, using that model fit as the mean and specifying also a standard deviation. In contrast to this linear model format, what a generalized linear model is doing is something actually quite similar. You'll see that there's really not much of a difference. Instead of predicting mu in the deterministic part, we're actually predicting some function of mu. This is the transformation right here. This could be the log of mu or some other kind of variant. And what this is known as is the link function. And this is a really important term to know when you're working with generalized linear models. The link function. Link is in reference to the link that is joining your data to the transformed data. The function that you're using to link those two, that's the link function. And so you'll see that the beta naught plus beta 1 times x sub I, it's still the same thing. The equation is still the same. We're simply adding a transformation on mu. And so then you plug in that transformed mu value to the probability distribution that produces your data. Now in this case, it's not necessarily a normal distribution. It could be any number of other distributions, Poisson, binomial, beta, anything. And so in a generalized linear model, right, your model fit is transformed with that link function, so it's not necessarily going to be a straight line anymore. It could be, but it might not be. And because then we're not specifying a normal distribution here in the stochastic part, but just some general type of distribution, it could be any number of distributions, the errors are not normally distributed necessarily. They could be, but they could also be distributed any number of other different ways. This is the family argument. So the error family is what this is referring to. The family is the probability distribution of your data. Another key term when you're working with GLMs, and we'll get into this when we start working with them in R. But you'll see here that the generalized linear model, right, as I said, it is just a generalized version of a linear model. If, for example, the function around mu in the deterministic part were an identity function, where it's just the same thing as mu, you might as well not even have a function there. And if the function on the probability distribution is a normal distribution, this generalized linear model becomes a linear model, right? If this is simply a more general formulation of a linear model that allows you to accommodate non-Gaussian probability distributions and model fits that are not necessarily straight lines. Now, fitting a GLM is also a little bit different than fitting an LM. We don't need to actually kind of do the math on this ourselves, but it does have important implications for us in understanding how to apply these different model types. So a linear model, an LM, when it fits itself to your data, it's doing so using a kind of mathematical operation where it minimizes the sum of the squared residuals, right? This is why it's sometimes called ordinary least squares regression. It's the minimizing of these squared residuals. So it's fitting itself, this red line here, to your data by trying to find the route that reduces the residuals as much as possible, the squared residuals, technically speaking. Now, this is a kind of simple mathematical formula that's pretty easy to do, which is why linear models do it. But it only really works if your data are normally distributed, if your residuals are normally distributed. Once we violate that assumption, we can't really use this sum of squared residuals approach. We need to use something different. And so GLMs, when they fit themselves to your data, are using what's called maximum likelihood estimation. Now, maximum likelihood estimation is way beyond the scope of this course, but it's important to at least understand generally what it is, basically what it is, and the implications that it has. And so maximum likelihood estimation is a process, a computational process, by which your model will search a bunch of different parameter values. It will search a range of parameter values and try to find the one or the ones that are most likely to produce your data. Right? Again, it's all about the probability of getting your data in a frequentist statistical paradigm. And so the maximum likelihood estimation is trying to find the parameter estimate that makes your data most likely to appear. That's all we're going to get into maximum likelihood estimation, but the implication of this is that in a linear model, p-values and r-squared values, these other important things, all kind of depend on assuming normality and that sum of squared residuals approach and some of these other assumptions. Once you kind of depart from that and you've moved into a generalized linear model with maximum likelihood estimation, you can't actually calculate p-values and r-squared values and such in the same way. And so we're going to need to do slightly different things with GLMs to calculate p-values and r-squared values, which aren't exactly the same as with LMs. But once we start working with GLMs in R, you'll see exactly how this plays out. And it's really not all that big a problem. It's just another consideration that we have to take into account.